Hi, I'm Brandy Heflin. I'm a personalized physics instructor, and I help high school and college students feel confident and successful in learning physics. A very common question that I get from my students, both when I was a teacher and now as a tutor, when they're studying kinematics is, how do I know how to choose the right equation? So I have for you today a very simple tool that you can use to correctly and accurately select the right equation when you are working one-dimensional kinematics problems. There are 5 kinematic variables that we use to describe a body's motion. First, there's the elapsed time, t. Oops, apparently I don't have my draw tool on. Give me just a moment. There we go. There's displacement, or change in position, which is delta x if it's a horizontal change in position, delta y if it's a vertical change. There's initial velocity, which you might see as v sub I or vi, or you might see it as v with a 0, which is pronounced v naught, as in NAUGHT, meaning nothing. There's final velocity, which you might see as v subscript f or vf. And then you might also see the final velocity as just plain old v with no subscript. And then there is the acceleration a. There are 2 important definitions to review. One is average velocity, where average velocity, the bar across the top tells us that it's average, is defined as the change in position for an object divided by the elapsed time. There's also average acceleration, which is defined as the change in instantaneous velocity divided by the elapsed time. So you might see this as v final minus v initial divided by our time interval. And I'll go ahead and write it as a t final minus a t initial. And there are 3 basic relationships among our 5 kinematic variables. Those are the change in position is equal to the initial velocity multiplied by the time, plus 1/2 times the average acceleration multiplied by the time squared. The next is final velocity equals initial velocity plus the average acceleration multiplied by the time. And last but not least is final velocity squared equals initial velocity squared plus 2 times the average acceleration multiplied by the displacement. And there's one more bonus equation that's not necessarily part of the standard set, but also works for a constant acceleration, which is 1/2 of the sum of initial velocity plus final velocity, all multiplied by the time. Knowing which equation to pick for a given problem is simply a matter of recognizing which variables are given and which one is being sought, or sometimes more than one is being looked for. And an easy organizational tool for this information is the following table, where we will list the time. Okay, I'm not sure why my pen tool is not drawing all of a sudden. We've got the time. We have displacement. We have initial velocity, we have final velocity, and last but not least, we have the average acceleration. And simply fill in what's given and then put a question mark for the quantity that's being sought. Let's work a few examples. Here in our first example, a car is going to accelerate from 12 meters per second to 25 meters per second in 6 seconds. What was its acceleration? So from 12 meters per second, that's an initial velocity, to 25 meters per second, that's a final velocity. In 6 seconds, that is a time. What was the acceleration? Let's put a big question mark in the box that we're looking for, and then we can always put an X in the box for the thing that we don't need, and then we can even cover it up. And that helps us see that we need the equation that has time, initial velocity, final velocity, and acceleration. The easiest equation for us to use is going to be v final equals v initial plus the average acceleration multiplied by the time. So let's substitute our given values. And then continue solving our problem here. And we get a value for the average acceleration of 2.16 repeating decimal meters per second squared. We could also have used the definition of average acceleration, which is change in velocity divided by the elapsed time. So for the second part of the question, how far did it travel? Well, we can carry down the given information that we had, and now we can also add in 2.16 meters per second squared for the acceleration, and we can put a question mark in the box for the thing we're finding. And at this point, we really can use any equation we like as long as it has displacement, time, initial velocity, and acceleration. We don't have to use the one with v final. So we have two options. And since it's not used as often, I'm going to use that bonus equation that was 1/2 times the quantity initial velocity plus final velocity and quantity multiplied by time. You could just as well have used b naught t plus 1/2 at squared. But what I like here is that this lets us solve this question even if we couldn't find the acceleration for some reason. And I get a value of 111 meters. In this next problem, a car is going to slow down from 20 meters per second to rest in a distance of 85 meters. So we're going to slow down from 20 meters per second, so that's going to be an initial velocity, to rest. This is one of those pieces of implied information. It doesn't give us a value, so we have to interpret that being at rest means 0 meters per second for the velocity. And that's going to happen in a distance of 85 meters. So we'll plug that in for delta x. What was its acceleration? Assumed to be constant. So we'll put a question mark in for acceleration, and we could put a big old X in for time because we simply aren't going to need time. We could cover up time if we wanted to, and that shows us that we're going to need the equation that has delta x, vi, v final, and acceleration. Sounds like we're going to be using v final squared equals v initial squared plus 2 times the acceleration times the displacement. So let's complete our substitution step. The acceleration is what we're going to find, so I don't actually need a parenthesis there. And then times the 85 meters. And so 0 squared equals 400 plus 170 times the acceleration. And actually, I could just leave this as 0. I don't need 0 squared. And so negative 400 equals 170 times my acceleration. And I get an acceleration of negative 2.35 meters per second squared. Well, how long did that take? We can now copy down all of the information that we have had so far. We have the 85 and the 20 and the 0, and now we can plug in this negative 2.35 meters per second squared for the acceleration, and then we can put a question mark in the box for time. So really, again, at this point, any equation is going to work that involves time. We could do delta x equals vit plus 1/2 at squared, but ooh, that has a t in it, or a squared in it. That's no fun. But maybe instead we want to do V final equals VI plus AT. It's definitely a way that I make decisions about what equation to use when I have several that could work. I go for the one that has the simplest math. So let's substitute. And I would actually add the 2.35t to both sides rather than subtracting 20 from both sides. Oops, I might want to remember my t there, because I don't like dealing with negative signs if I can avoid them. All right, and so here at the end, we get t equals 0.51 seconds. And for our last problem, now we have some vertical motion. That tells us that our acceleration is going to be due to gravity, because we've got this helicopter that's ascending vertically with a speed of 5.5 meters per second, and then at a height of 105 meters, a package is dropped from a window. So the package is moving upward with the helicopter, and then it's going to fall down. So I've oriented my table vertically to indicate that it's vertical motion, and it's a given, or like implied information, I should say, that we're going to use the acceleration due to gravity of negative 9.8 meters per second squared. And actually, let's just make it 9.8. There we go. So that 5.5 meters per second, that is how fast our package is going to be moving, because it's moving along with the helicopter upward. And then what do we do with this 105 meters? So we've got the ground, and we've got this helicopter. You know, try and draw some rotors here. And it's moving upward with a velocity, VI, of 5.50 meters per second. And we're going to have this package dropped out the window. So the package is initially going to keep moving upward, and it's going to slow down and come to a stop. And then it's going to end up 105 meters below where it started. So we're not asked how high does it go. All that matters here is that the package is ending 105 meters below where it was released. So when we talk about that vertical displacement, we're comparing what was the starting position of the thing to what's the ending position. And so we will make this a negative 105 meters. And we're asked how much time does it take, so we'll put a question mark in for time. And then we can put an X through final velocity, because we're not asked about final velocity just yet. And this guides us to an equation that has time, delta y, vi, and a. So there's only one that fits the bill. Delta y equals vit plus a half a t squared. So we will make our substitutions. And you might be noticing that this is shaping up to not look so pretty. It is a quadratic relationship, and we are going to have to solve either using the quadratic formula, or my personal preference is plot that equation and get the zeros. Use the graphing calculator to get the zeros. But I did solve it both ways, and when I do b squared minus the square root, or sorry, negative b plus, let's start again there. When I do negative b minus the square root of b squared minus 4ac, I get a time of 5.224 seconds. And when I add the square root on the top, I get negative 4.102 seconds. And so in physics, we've got to think about which of those actually makes sense. Clearly, the positive one is the value that makes sense, because this negative time is before the package was released. That is what a negative time would mean in physics. So we'll say before it fell. So we'll want to take that positive value for the time. And for part B, how fast is the package moving just before impact? I didn't redo the table here, but we're going to want an equation that involves V final, and the simplest one is going to be VI plus AT. There's no, we could have done delta x equals 1/2 times the quantity VI plus V final times T to solve for V final, but it's inside the parentheses and there's a half. We could do V final squared equals V initial squared plus 2A times the displacement, but there are squareds. No, thank you. Let's just go for the one that is the simplest equation, which is going to be V final equals 5.5 minus 9.8 times that 5.224 seconds. And I will get a final velocity of negative 45.7 meters per second. And let's check, does that make sense? Our package is initially moving upward. When somebody drops it out the window, it's going to continue moving upward as it slows down. It'll stop at the top and then it's going to fall. And that negative 45.7 meters per second is indicating that our package is moving down. So that value is consistent with what physically makes sense. So I hope you have enjoyed this simple tool for solving kinematics problems. If you have a video solution request that you would like me to put on my YouTube channel, or a particular introductory physics topic that you'd like a short lecture on, you can send that to physicsproblemrequests@gmail.com. If you would like some assistance via email, you can use freephysicshelpline@gmail.com. There is a limit of 10 questions per academic year. If you want to learn more about my services, you can email me at brandyheflinphysics@gmail.com. You can visit my website, virtualphysicsofficehours.com, or you can find me on Facebook. I'm Physics Tutor Brandy. I love physics, and I love helping you. Until next time.